Okay, so already Fabio said the title of my talk, and I want to thank first of all the institutions that support our investigation here in Argentina, which is the National University of La Plata, CONICET, Agencia, and the Inter-American Open University. I start to talk about diabetic cardiomyopathy because it's a very well defined entity in diabetic population. And if you look for diabetic cardiomyopathy in PubMed, you can reach more than 4,000 works. So it's very well studied entity. In a recent, very elegant review in Circulation Research from 2018, the authors established that they not established, they just say and put in knowledge of everyone that hyperglycemia, insulin resistance, and hyperinsulinemia is leading to cardiac insulin resistance and metabolic disorder. And all these factors, mitochondrial dysfunction, inflammation, oxidative stress, autonomic neuropathy, endoplasmic reticulum stress, and apoptosis, evolve to cardiac stiffness, hypertrophy, and fibrosis. So, and this is the cause of diastolic dysfunction and systolic dysfunction leading in heart failure. This is at whole body level, but at heart level and at cellular level, we already know that in diabetic cardiomyopathy, there is a remodeling of action potential, and also there is a decrease in calcium transient and prolonged calcium transient signals. And this is at least because CaMKII protein in the sarcoplasmic reticulum is decreased, phospholamban is increased, and its phosphorylation is decreased. So the reuptake of calcium in these myocytes are very low, and then the sarcoplasmic calcium content is decreasing. Moreover, there is a leak from ryanodine receptors 2, and this calcium is promoting apoptosis or arrhythmias or every disorders in diabetic cardiomyopathy. Moreover, in mitochondria, it's already established that calcium can go up or go down, and if it's going down, decrease the potential of mitochondria to as a fuel source, as an energy source, and moreover increase reactive oxygen species. Thus, calcium mishandling can conduct to action potential remodeling, endoplasmic reticulum stress, arrhythmias, hypertrophy, impaired inotropy, impaired lucitropy, decreased energy production, apoptosis, autophagia, mitochondrial fusion or fission, increased oxidative stress. And I think that I can go on with this list for several slides more. But in the stage of glucose mishandling, I think that we could classify different stages in this metabolic disease. The last step is diabetes mellitus type 2. That is a chronic metabolic disease characterized by hyperglycemia due to deficiency in the production and or in the action of the insulin. Diabetic cardiomyopathy, DC, is one of the major complications, and usually the bad controller patients present diabetic cardiomyopathy and heart failure. So there is an intermediate stage that is the metabolic syndrome that is characterized by the presence of prediabetes and other comorbidities like hypertension, obesity, or dyslipidemia. And here, the myocardium compromise is multifactorial. But at the beginning, early in the beginning, there is the prediabetic stage. So prediabetes precedes diabetes and metabolic syndrome, and is characterized by impaired glucose tolerance and or altered fasting glucose. And this condition is the first step in the type 2 diabetes mellitus evolution. It's asymptomatic and its finding is random. And it is very important because it's not usually diagnosticated, because you don't have signs or symptoms of prediabetes. So, which is the origin of diabetic cardiomyopathy? That's our question. And if we look for prediabetes and heart with the same criteria as diabetic cardiomyopathy, we have a much less work output in PubMed. And this is because it's very difficult to diagnose it, because as I told you, you have no symptoms or signs that you can think that you have prediabetes. So we focus on the typical proteins of easy coupling that are already discussed and described in diabetic cardiomyopathy, but in a pre-diabetic model. And I think that with our results are very surprising, because our model is it's very short and it's very early in the national evolution of the disease. So, and in the last slides, I'm going to show you some results that are magnify the mitochondria function and role in this pre-diabetic stage. Thus, our pre-diabetic model was made in Wistar, in male Wistar rats, and in mice C57 as wild type, and SRAIP and AC3I mice. The AC3I mice express the CaMKII inhibitor peptide AC3 at the cardiac level, and was given by Mark Anderson lab several years ago, and we worked with him and with his collaboration. And we also use SRAIP mice, which express the peptide AIP, a CaMKII inhibitor targeted to the SR membranes. And this peptide has a tail that's anchored in the SR membranes, and then CaMKII2, the kinase calcium calmone independent, cannot phosphorylate its target in the sarcoplasmic reticulum. All the groups were fed with controlled diet or with fructose-rich diet. The fructose-rich diet is the water enriched with 10% of fructose ad libitum for 21 days. I mean 3 weeks. And this model is not made by us. It was also used by other laboratories, and it's already proved that performs prediabetes. So after the 3 weeks, we isolate myocytes, mitochondria, and make cardiac homogenates and perform the experiments. The first that I want to tell you is the metabolic characterization of the animals. The rats, we can measure a lot of parameters, and we detect hyperinsulinemia in the treated group, high triglyceridemia. They have higher non-esterified fatty acids, a higher HOMA rate. The fasting glucose was not different between the control and the treated group. The area under the curve after an intraperitoneal tolerance glucose test was higher in the treated group. The body weight was not different, so the animals have no obesity, and the blood pressure was also not different. So we think that this is very important because the animals doesn't have a pressure overload or volume overload condition to the heart. So we think that the results that I'm gonna show you in the myocytes are property to the myocytes and not to other comorbidities due to the model. So in the mice, we could measure the fasting glucose, the area under the curve, and the blood pressure, and they behave similar to the rats. So we perform echocardiograms, and we detect a systolic dysfunction because we have a lower fractional shortening, but also we have a hypertrophy and dilation of the chamber. So this was very surprising for us because the treatment is very short. So we decided to isolate myocytes to see the behavior of the cells, of the heart cells, and here you can see the protocol that we used. We measure intracellular calcium with FURA2 by epifluorescence, and here we submit the cells at quiescent state, and then we start to feed stimulated at 1 heart, and then we made a caffeine pulse to measure sarcoplasmic reticulum content. And then we repeat the protocol under adrenergic stimulation with isoproterenol, and we can see in control cells that there is a normal calcium baseline and normal bit-to-bit calcium transients, and they are enhanced with isoproterenol stimulation. But when we examine the myocytes from fructose-treated hearts, we can see that in quiescent condition they have a spontaneous calcium release events, and even in between the beats you can see release of calcium. So, and this is magnified when it's submitted to adrenergic stimulation. So we go deep into these spontaneous calcium release events, and we examine them under confocal microscopy, and we can see that the sparks frequency is not different between the groups, but we have several ways that are so pronounced that finish in a spontaneous calcium transient, which make possible a spontaneous contraction, and this is magnified by isoproterenol. So, because as Fabio say, we have a history with CaMKII, and because CaMKII is involved in several heart diseases like the evolution from hypertrophy to heart failure, apoptosis, arrhythmias, and etc. We suspect that CaMKII could be involved in these spontaneous calcium release events, and then we use this specific inhibitor of CaMKII, KN93, and we could detect that under the inhibition of CaMKII, the fructose-treated myocyte did not present any spontaneous calcium release events in quiescent conditions or even when they are passive. And moreover, they are not magnified or unmasked any spontaneous calcium release event when it's submitted to adrenergic stimulation. We compare this results with the inactive analog of CaMKII, CaMKII, and we could see here the spontaneous calcium release events at quiescent conditions or even when the cells are phased. And because one of the targets of CaMKII is Ryan receptor 2, and is a very important protein in the EC coupling, we looked for the phosphorylation of this protein at the CaMKII sites and on the pKa sites. So we could detect that the expression of the total Ryan receptor 2 are not modified under the diet, but when we examine the serine 2814 site of Ryan receptor 2, we can detect an increase in phosphorylation under the fructose-rich diet. And when this is in cardiac homogenates, and so when we examine the pKa site, the serine 2808, we cannot detect any modification. CaMKII can activated by increasing calcium, by oxidative stress, by nitrosylation, by glycosylation. So at that point, we start to look for the oxidation of the enzyme, and we could detect that in our model, we have an increase in oxidative stress detected by T-bars or by the elucidating method, and moreover, we have an increase in the oxidation of the enzyme in our model. So we thought that CaMKII is oxidizing by the metabolisms of this fructose-rich diet, and then is phosphorylating Ryan receptor, making the SR leaky. So we co-treated the mice with Tempol, which is a scavenger of reactive oxygen species, and we could detect that in these mice treated with fructose-rich diet, the co-treatment with Tempol decreased the oxidative stress and also avoid or prevent the spontaneous calcium release events, as we can see in these confocal pictures. So then we used the SR-AIP mice, and these mice which have the peptide AIP, which is an CaMKII inhibitor targeted to the SR membranes, or also have an increase in oxidative stress that could be prevented by Tempol, but without Tempol, there is no spontaneous calcium release events. So that means that reactive oxygen species is production is upstream CaMKII activation. Of course, when co-treated the animals with Tempol, we don't have any spontaneous calcium release event. So we wanted to check in another model of CaMKII inhibition if we can prevent these spontaneous calcium release events. And we can see here again that in wild-type mice, the fructose-rich diet induce sparks, waves, and spontaneous contractions in these confocal images. And when we use the AC3I mice, which express the inhibitor AC3 at the whole heart level, we don't have any spontaneous calcium release events. And we have here the overall results of this experiment. So emphasizing in the role of ryanodine receptors, we performed some experiments in a cell model in HEC cells expressing wild-type ryanodine receptor, and we submitted the cells, or we cultured the cells under high glucose conditions or low glucose conditions. So when we check by ryanodine binding assays the ryanodine activity, we can see that the high glucose conditions make the receptor with more activity, and this is the overall results of the maximal activity of the receptors. And here you can see that there is a greater activity of the receptor under high glucose conditions. Then when we use the inactive analog of the inhibitor of CaMKII, KN92, we have the same behavior as the high glucose alone. But when we use high glucose and KN93, the inhibitor of CaMKII, we can lower the levels of ryanodine receptor activity to low glucose levels. We check in this model the phosphorylation of the ryanodine receptor, and we can see that the PK8 site, the serine 2808, is not modified by high glucose. And then when we check the phosphorylation site of CaMKII, the serine 2814, we can see behavior similar as you see in the mice. So we could check. We wanted to check if this behavior is also in our animals, and so we perform ryanodine binding assays from our wild-type control diet animals and wild-type FRD or fructose-rich diet animals, and we can see that these animals treated with fructose have also an increase in ryanodine activity, and this is the overall result of this experiment. So all these results conduct to arrhythmias, because we could check by performing ECGs in the mice that fructose-rich diet in the wild-type mice induce even bradycardia, bidirectional tachycardia, ectopic beats, or AV blocks. And this kind of arrhythmias could be avoided in SRIP mice, which have the inhibitor peptide targeted to the SR membrane. So at this point, we have some conclusions, and we could say that reactive oxygen species in the prediabetic model are increased. So, and these reactive oxygen species are activating CaMKII, and CaMKII is phosphorylating ryanodine receptors, which make the SR leaky, and this calcium is promoting arrhythmia. So in the next step, we wanted to see if this calcium leaky by the SR is going through the mitochondria and increase mitochondrial calcium content, and see what happened with the relationship between mitochondria and the sarcoplasmic reticulum. So, because apoptosis is also a phenomenon saw in diabetic cardiomyopathy, we look for this phenomenon in our prediabetic model, and we can see that the FRD treated hearts has increased apoptosis, and this apoptosis could be prevented by tenfold. So these experiments tell us that the same pathway that it's promoting arrhythmias is also promoting apoptosis. And usually apoptosis in the heart is mediated by a mitochondrial pathway. So here are the overall results of this photograph. And we also measure apoptosis by the BAX-BCL2 ratio, and we could confirm that pro-apoptotic proteins are increased over the anti-apoptotic proteins. So taking in mind that mitochondria is involved in this apoptosis, we measure mitochondrial swelling in isolated mitochondria from fructose-rich diet mice, and we can see that there is an increased swelling in these mitochondria. Moreover, we measure mitochondrial membrane potential by CaMKII dye in isolated myocytes, and we can see here that this dye is green when the mitochondria is depolarized, and it's red when the mitochondria is hyperpolarized. And in the myocytes from fructose-rich diet hearts, the green signal increase and the red signal decrease, telling us that mitochondria from these myocytes are more depolarized than in control diet mice. So we recheck the relation, the distance between the sarcoplasmic reticulum, here skeletonized in blue, with respect to mitochondria, and we can see here in orange the space between mitochondria and sarcoplasmic reticulum. And in wild-type mice, the diet of with richer fructose decrease this space or this distance between the sarcoplasmic reticulum and the mitochondria. And this is significantly statistically significant, the closer proximity. So when we examine the AC3R mice, we cannot see any difference between the control diet and the FRD diet at the level of the distance between the sarcoplasmic reticulum and the mitochondria. Because this space is a very important microdomain where the calcium concentrates and could reach very high levels, and it's very controlled by several proteins. We wanted to examine mitofuscin 2, CRP75, and BDAC. These three proteins are involved in tether the sarcoplasmic reticulum to the mitochondria, and that's why we look for them in this Western blot. And we can see here that in wild-type mice fed with fructose-rich diet have an increase in the expression of mitofuscin 2, CRP75, or BDAC. And this expression is not evident in AC3I mice. This is a very preliminary studies, and it's the ongoing research right now. But these results are promising to us and tell that CaMKII is really involved in this proximity, and maybe this proximity is due to this enhance these proteins. So the closer relationship between sarcoplasmic reticulum and mitochondria could favor the traffic of calcium from sarcoplasmic reticulum to the mitochondria and overload the mitochondria with calcium. Thus, we perform this kind of experiments in which we measure extra mitochondrial calcium in isolated mitochondria with 5N calcium green dye. So we added calcium pulse, and then that's reflected in these peaks of calcium of the signal of the dye, and then the decay is represented by the calcium reuptake by the mitochondria. But when the mitochondria cannot accept any more calcium because it's saturated, the MPTP opens and then this calcium signal rises abruptly. So we can see here that the fructose-rich diet mice reach this point much early than the control diet mitochondria. And in the overall results, we have a significant decrease in the calcium retention capacity of these mitochondria. We have very few experiments in AC3I mice, but at least at this point is not significantly different. So we think that if we could increment the number of experiments, maybe we'll have promising results about CaMKII involved in this phenomenon. With this result, we turn it to mitochondrial morphology in the prediabetic model, and we can see that fructose-rich diets induce the mitochondria became more round, more tiny, and there are more density of this of the mitochondria in the prediabetic heart. So again, in the AC3I mice, there is no changes in these parameters, indicating that maybe CaMKII is involved in this in these changes. And because we see these results, and because the mitochondria seems to be more with more calcium inside, we thought that maybe fission process is occurring in this model. So we examined the DRP protein, which is the main protein involved in fission, in mitochondrial fission, and we could see that in wild-type mice there is an increase in the DRP expression under the fructose-rich diet, and this is not happened in the AC3I mice. Moreover, the OPA1, which is the main protein inducing fusion, is not changed under the diet, so we think that fission is prevailing over fusion in this model. So as conclusion and perspectives too, we have that CaMKII is phosphorylating the RYRs2, and this is liberating the calcium and making more calcium going through the microdomain between mitochondria and sarcoplasmic reticulum, and this calcium is going inside the mitochondria. Moreover, this phenomenon is enhanced by a mitofusin, by the overexpression of mitofusin and GRP75, and we don't know if this increase in expression of these proteins is mediated by CaMKII or by calcium or by other proteins that we are not studying in this project, but it's an ongoing research right now. And then we speculate that peroxygen production by the mitochondria is making a vicious cycling between the oxygen peroxide, CaMKII activation, and more calcium in this microdomain, and go on. Moreover, there is a fission of the mitochondria due to the overexpression of DRP, and DRP could be phosphorylated by CaMKII or by other proteins that we don't have studied yet. So thank you very much for your attention. This is the team that is working with me, Marilyn Federico. She's running all the experiments. Mike Zavala is performing the Western roads and other experiments, and also Sofia Lopez and Tamara Vico are working very hard in this project. And this is all the people that collaborate and enrich this investigation. So thank you very much for your attention, and be safe and stay at home.
Very much, my dear Julieta. It was very interesting, and I appreciated very much the way you presented this large amount of data and putting together established findings with new findings that you still have to make causal relationships. I mean, at this point, you produce very interesting observations, but I wonder, and we will see this in the discussion, how much is a cause and a consequence of oxidative stress and CaMKII activity. But your data on mitochondria are quite interesting, and you left the interpretation hypothesis for the end. So you presented the data and after the hypothesis, and this is nice because sometimes people try to put the hypothesis more than the data, and this is not good, especially at your young age. And also I appreciated very much that this work was produced in your country by young women, and this is absolutely beautiful. So thank you very much. I enjoyed this presentation very much, and now I leave the floor again to you to handle the many questions that I'm seeing appearing in the question and answer box. So it's up to you.
Okay, so thank you, Fabio, for your comments. Let me see the questions. So Constantino.
So it's nice if you tell us the name of the people that is asking question, and then you try to give your answer and your opinion and comment.
Okay, so Constantinos Drosatos said, as glucose uptake in the heart relies on both insulin-dependent GLUT4 and insulin-independent GLUT1 glucose transporters, what is the extent that early stage of diabetes cardiomyopathy can be attributed to excess glucose due to hyperglycemia uptake? Well, I don't know. The first thing is I don't know, because we didn't measure GLUT1 or GLUT4, but we measure at some time sodium inside in the pre-diabetic model, and we have a higher sodium, cytosolic sodium, than in control diet mice. So, and the other thing is that hyperglycemia in the pre-diabetic model is not constant, so only is detected under the intraperitoneal tolerance glucose test. So we don't know exactly, but you can think that both gluts are mainly involved. The other thing is that when we made experiments in isolated myocytes, we don't use insulin in the buffer. So I think that the insulin-dependent glut is not working at that point. So why you use fructose-rich diet in your study? This is Himi Tripathi. So because it was an already established model of prediabetes, it's easy, it's cheap, and it's short. So
sorry, Julieta, there is another part of the question, if you read it completely, because this colleague is putting the question that you, in this case, you have diabetes and obesity together.
Excuse me? Where? Glucose transporter. What's the
repeat
test?
it twice. Yeah.
Can be attributed to excess of glucose due to hyperglycemia state? Well, I think no. I think no, because the hyperglycemia is not constant. So I think no. Okay.
You can get obese mice, no?
No, the mice are not obese. The mice
I remember that the weight was not different.
Yeah, the mice, the model have no obese and have not high blood pressure, hypertensive. They are not hypertensive, and that's it's very important to us because they have no comorbidities to indicate that they are pressure overload or volume overload. So, Jima Resultado, have you observed any difference in phosphorylation of serum 2013? No, we didn't. I'm sorry. This is that we want to check, but we don't know. Glucose-induced Viva Rani. Glucose-induced RAS production is, and this is incomplete.
Incomplete answer. You can skip it and go to the next one. That is quite
Philip Eaton asks, temple is used as superoxide. This mutates mimetic catalyzing conversion of superoxide to the oxygen hydrogen peroxide. So why do you argue that the effect of temple is by reducing oxidative stress when it may promote oxidation of targets by hydrogen peroxide? Well, when we check T-bars under the temple treatment, and we decrease the T-bars value, that is lipid. T-bars is an index of lipid peroxidation, and temple reduced this lipid peroxidation. So we didn't check exactly oxygen, hydrogen peroxide or superoxide, but we think that we are decreasing oxidative stress because lipid peroxidation is reducing with the co-treatment of temple. Emiliano Diez, hi Emiliano, he's a colleague of us. How did you explain the daily blocks in fructose-fed animals? No, I don't know. I mean, we perform ECG in the mice, and we found that the mice that receive the fructose treatment have at least one type of arrhythmia. Some mice have bradycardia, some mice have bidirectional tachycardia, some mice have AV blocks, and some mice have ectopic beats. That was not very uniform. The presence of the arrhythmia. I mean, there were arrhythmias in the mice, but the arrhythmias, the type of arrhythmia, was not uniform in all the mice. Rosanna Bassani, hi Rosanna. She said, thank you. Do you attribute the spontaneous activity in the high fructose fed group solely to increase the calcium leak? Have you investigated other sarcolemma possibly contributing mechanisms? No, we don't. We check the SR calcium content, and the SR calcium content is decreased, and we think that it's decreased because the radianalin receptor phosphorylation, and because the SR is leaky, that's why the SR calcium content is decreasing. But we don't know investigate other sarcolemma possibilities. I think that the NCX is involved because the calcium leaky by the SR should be drained by the NCX. So thank you, Rosanna. Sina Haipur, given the prediabetes often occurs in a constellation with hypertension and dyslipidemia, how do you think these comorbidities could affect this finding? Well, as I told you, we don't have hypertension. We have dyslipidemia, and I have some transmission electron microscopy photograph that show you drops of fat, but we don't have hypertension. So maybe dyslipidemia is affecting the results, but we don't check it. Marisol Luis Meana, fructose is a prominent source of age. Yeah. To what extent the observed change in renin receptor gating properties in the fructose-fed animals could be the consequence of the renin receptor glycation? We have recently observed that the renin receptor 2 is indeed an important target of advanced glycation in the context of aging. Yes, could be. I mean, that is very possible, but the thing is that when we use Tempol, or when we use CaMKII 2 inhibitor, or when we use transgenic mice with CaMKII 2 inhibition, we can avoid spontaneous calcium release events. So we really think that the pathway is CaMKII 2, which phosphorylates renin receptor, and maybe glycation is present, but the CaMKII 2 activation is more important at this point. Daniel Johnson. I was wondering if the FRD diet model, when you induce a spontaneous calcium release with isopotent, did you also look at location number of beta-adrenergic receptors and how this may be altered? No, I didn't, sorry. No, but it's very interesting, because if you see the response to beta-adrenergic stimulation, the fructose-rich diet has a blunted response. So it could be possible that the receptors are downregulated or something like that. Shuriana Aguilar. Hi, Shuriana. Okay. CaMKII 2 also affects cell-type calcium current, which could increase calcium-induced calcium release and explain why you see more renin receptor opening, aside from phosphorylation by CaMKII 2. Have you done any cell-type calcium current measurements? No, I didn't, sorry. But
do you mind if I just interject here quickly? So,
okay.
The KN93, I believe, also can, at higher concentrations, block some of the L-type calcium channels. So have you used KN92 maybe as a control?
Yes, well, I showed you.
But in the calcium experiments?
Yeah.
Okay. And you didn't have any effects there?
And when I put KN92, I have the same behavior as nothing, as I put fructose alone. So, and when I put KN93, I can abolish the spontaneous calcium release events. We measure that in by epifluorescence, by confocal microscopy, but we did not make experiments like ryanodine binding assay or I mean in the bulk calcium, in the cytosolic calcium, KN92 doesn't affect the effects of high glucose, high fructose. Okay, Rosanna Bastani again. In ACSVI mitochondria, even if the maximal calcium load is similar in control and in fructose diet? I don't understand very well the question. Sorry. Okay.
No,
Can I see the
yeah, you have to read below.
Yeah.
Okay.
Yeah. Even if the maximal calcium load is similar in control and FRD preparations, calcium uptake seems to be considerably slower in the later during the calcium pulses. What do you think is going on? Okay, so we have very few experiments in the AT3I mitochondria. So we have to repeat them and have any good conclusion, because at least we don't have difference, but we have a lot of dispersion of experiments. So these are very preliminary, and I show you because it's in the line with the other experiments. So we think that CaMKII is involved in this calcium retention capacity, but we are not sure. So Hector Chapoy, what do you think about the low CRC in FRD mitochondria? Is because MCU is
overexpressed,
or what happening with other components of Uniplex? We could not examine MCU, but we examine the BDAC. So BDAC is overexpressed, and BDAC is has also the function of tether the mitochondria with the CRP75, but also to enter calcium to the mitochondria. So I think that FRD mitochondria, it's calcium overload. So that's why it has less calcium retention capacity, because it's already full of calcium. But we have to check, we wanted to check the MCU expression and see, and we also want to check the expression in membrane associated mitochondrial membrane associated, because we check it in homogenates, and this is this protein translocates from the cytosol to this microdomain, so could be different. Fabio, you want to say something?
No. There was the connection was unstable. Now it's stable again.
Okay.
We lost you for a few seconds. That was the problem.
Okay, so Dunha, well, I don't know how to say this last name. Thank you, Fabio. Did enhanced mitochondrial calcium content affect oxidative phosphorylation, ATP provision in your pre-diabetic model? We have preliminary results that I didn't want to show you because we are not very sure, but we have greater oxygen consumption in stage 4 of the mitochondrial metabolism. We don't have any change in the ATP production, but we have an increase in oxygen peroxide. So we think that maybe in the pre-diabetic mitochondria, the enhanced oxygen consumption is inducing superoxide, and this superoxide is dismutated to other hydrogen peroxide, and then the electronic change transport could be uncoupled. This is what we think, but we have very few experiments, and we don't know exactly what is happening with the metabolism, but it's our impression. Emma Robinson, in the Wister rat model, you show no significant body mass change. In the mice, you didn't. Given the role of lipid droplet-associated regulation of HDAC and CaMKII in the diabetic heart from the dyslipidemia, do you analyze further the lipid profile in the heart or blood and correlate that with CaMKII relation? No, I didn't. So we know that there is no difference in the body mass with the treatment, but we also know that for another laboratories that use the diet, that they have a different profile of visceral lipid tissue. So they have a hyperplasia, and they have different adipokines that are liberated that are released by this fatty acid, but this fatty tissue. So we don't know the association between, and we couldn't measure the lipid profile in mice because the bulimia of the mice is very small. But we think that this lipid profile is not affecting our results, specifically because we have changes with CaMKII inhibition and not with any anti-lipids or cibastatin or something like that. I mean, we didn't check it, but it's our impression. So, Viva Rani. Recent studies show that not every ROS species is upregulated during stress. The effects might be species specific. Do you look for intracellular redox dynamics in your notes? We check in the isolated mitochondria the oxygen peroxide production, and it's higher, but that's all. And we also check in rats, in cardiac homogenates, the lipid peroxidation and superoxide production by elucidating, and it's higher with the diet, but but with no effects between other ROS species or any nitrogen oxygen species that which also maybe are modified by the diet. Shita Birak, nice. Have you observed difference in the mitochondrial morphology, morphometric measures in subsarcolemmal versus intramyofibrillar population? No, we didn't check that. Now Marilyn is in laboratory of Dr. Shei Xu, and she's learning about this separation of distinct population of mitochondria. So maybe in the next few months, if she come back, we can check that. Gema again, why your candidate would be oxygen peroxide and not other oxygen nitroside or others? Well, it's because it was that we can measure, but I'm sure that nitrogen reactive species are also compromised in this model. David Eisner, hi David. You highlighted the importance of increased RYR opening. Increased RYR opening also occurs in category and CPVT, often due to RYR mutations. In CPVT, the effects can be antagonized by agents that decrease RYR opening. Have you looked at the action of such compounds in your mind? No, I didn't. I can check the gating properties of the RYR, but when you made the microsomes preparations, I don't know if you lose some of the properties of the RYR that are in the whole cell or in the whole heart. So, but the answer is, excuse me,
what David was suggesting is if you tried any of these compounds you know, in your cells isolated from the mice or the rats, probably, I suspect.
No, I didn't. No, I didn't. But I don't remember the exact site, but there is a site that Silvia Priori discovered several years ago that is CaMKII 2 dependent site for CPVT. So, and I performed a few experiments in head cells overexpressing this mutation and exposed to high glucose. And they have a more ryanine receptor binding, ryanine binding assays. So they have more activity. But I didn't prove the compounds. That's the answer. Okay, Emiliano Medreira again. What about MIT respiratory function in your model? Did you measure cytokines in this model? What about oxygen peroxide production? Is related to CaMKII 2 also? Wow, too many questions in one. Okay. So, Fabio?
No, these are too many questions in one question. I mean, too many points.
Yes. Yeah, okay. So the respiratory functions, as I told you, we measure stage 4 and oxygen consumption is in stage 4 and in stage 3, and it's increasing in stage 4 but not in stage 3. That this is the control respiratory rate. It's decreasing, so indicating that maybe the electron change transport is uncoupled, but we are not sure. We have to make more experiments. That's why I didn't show you. And the other thing is that we have more production of oxygen peroxide, and oxygen peroxide overload is it's already known that can activate also CaMKII 2. So that's why I put like a speculation that this production of oxygen peroxide would activate CaMKII 2 and then make a vicious cycle that never ends. I mean, you have to stop it at some point. I don't know if I
put a comment on this. If I can put a sort of word of caution on this, because this is related also to questions that come afterwards, and so you can also breathe a little bit. You can respire.
Yes.
So
thank you.
In my experience, and as far as I know, if you start from a damaged myocyte, you will get damaged mitochondria. This doesn't mean that the mitochondria are not working properly inside myocytes and are contributed to the damage. To know this, you have to examine, you have to evaluate mitochondrial function in intact cells or intact hearts. So the isolated mitochondria can still provide a lot of information, but are not the proper preparation to establish a connection between mitochondrial function and the given pathophysiological entity in vivo. Okay, this is a common, not a mistake, it's a common misleading fact. So to give interpretation from the study of isolated mitochondria to what happened in vivo. Okay.
Well, we measure the mitochondrial membrane potential in isolated myocytes, but I think that is, as you say, Fabio.
But again, you isolated myocytes from the damaged heart. You should have a model in vitro where you recapitulate what you see in vivo on isolated cells, and then you can study mitochondrial membrane potential, the pore opening, calcium transport, and so on and so forth. Otherwise, you put together pieces of information that are not related to each other. This is the problem.
So do you suggest that we have to measure mitochondrial metabolism in the whole heart?
Well, that could be another aspect that you didn't consider. I mean, that another question would be how much CaMKII 2 has to do with the changes in metabolism that affect the diabetic heart, because we know that there is a reduction of glucose oxidation and an increase in fatty acid oxidation. Does this also depend on CaMKII activity, or CaMKII activity is a sort of consequence of this metabolic remodeling? But I mean, I'm not asking you because you already measure a lot of things, and there are obviously another 1,000 of things to be measured, and this is what they are keep nailing you on with questions. But please go ahead. I don't want to take any more space.
No, but it's a very nice suggestion. Thank you, Fabio.
This is a general remark. Okay.
So Heinrich Stadtmeier, I noticed lipid droplets in the FRD electromyograph. Did the FRD alter de novo hepatic fatty acid synthesis? I don't know. I'm sure that the visceral fatty tissue is compromised in the fructose-rich diet. But again, the model had no obesity. Gaetano Santulli, especially the data on SR mitochondrial distance reduced in FRD are really terrific. Do you have any data, or do you expect any change on mitochondrial function? Seahorse. Well, yes. Yes, we expect to have more calcium overload, mitochondrial calcium overload, and we also expect to have alterations in the metabolisms, and we have that preliminary.
Gaetano is asking exactly what I pointed out. So seahorse is a way to measure oxygen consumption in intact cells. So not to isolate mitochondria, but to measure oxygen consumption in cells subjected to high fructose, high glucose, and whatsoever. And this is much closer to the in vivo situation than isolated mitochondria.
Yeah, no, we didn't. No, we just could the isolated mitochondria. So Danja, then again, this
Danji Aksenchevich.
Okay. In your experimental model table, I didn't notice fasting hyperglycemia in any of your models. When you refer to high glucose used in your experiments, which concentration of glucose did you use? How did it compare to your measured circulating levels? No, I mean, I think these animals, the treated animals, doesn't have a continuous hyperglycemia, and the other thing, and they eat and drink ad libitum. So they, I cannot when we make the blood measurements, we put the animals in fasting, and then for around 8 hours, and then we make the measurement. When we made the experiments, we used 2 grams per liter, 10 grams per liter of glucose. And then we have another set of experiments that with high glucose, we have arrhythmias and apoptosis also, but this is another ongoing project. But I think that we want to examine in this model, it's what's happening with the myelocytes, the calcium handling, and the mitochondria at one established glucose level. So we performed experiments without insulin and with 10 grams per liter of glucose. So, and we don't change that. And this is not referring to the glucose levels in blood in the animals. It's a way what we do the experiments just to see how the cells behave.
Mm-hmm.
Okay, Shinsei Shu. Hi, Shay. My fellow is there, so I miss her a lot. You didn't mention about the role of energetics in the model. Did you measure the ATP or respiration? Yes. Yes, I didn't mention because we have very preliminary studies, results, so I'm not very sure about that. As I told above, we measure state 4 and state 3 of oxygen consumption in isolated mitochondria, and the oxygen consumption is elevated in state 4 in the treated mitochondria, and the ATP production didn't change between the control and fructose-rich diet mitochondria, and the oxygen peroxide is increasing. So we think that the electron change transport is uncoupled, and then the excess of oxygen consumption is going to form hydrogen peroxide, and this is why we have more hydrogen peroxide. But the ATP production is not altered by the diet. Okay, Maria Fernandez. Hi, Maria. Maria also collaborates with us sometimes. Maria says, I'm wondering if the increased oxidative stress can induce any other post-translational changes in the oxidative state of RYR2. Also contributed to increased spontaneous calcium release. Well, as I already said, that is possible, but the fact is that when we inhibit CaMKII 2, we can abolish the spontaneous calcium release events, the apoptosis, the arrhythmias, and all the pathway. So that if there are any other post-translational change, is less important than CaMKII 2 phosphorylation. Shawan, have you tried CaMKII in FRD model compared to CaMKII to analyze cardiac function at the in vivo level? No, we didn't. And this because it's very expensive to treat animals with that compound. We have not the sources to do that. But I think that it's more specific the transgenic mice. But I'm not sure. Nina Kaluderic.
I may know her.
Excuse me?
No. She works with me. I know her very well. Kaluderci.
Okay. Did you look specifically where within the cell rods are being produced? No, but we think that it's in the mitochondria. But we need to also block NOx3 or NOx4 to see if there is not pH at the sarcolemma. We don't know. Magali Samia El Hayek. What is the high glucose concentration used in the binding and Western blot experiments? Please. The high glucose in the cell model. Okay, in the cell model we use the standard media has 4.5 grams per liter of glucose, and the low level glucose was 1 gram per liter, I think. That's two commercial kind of media that are available in the source. So Helen Collins, I may have missed it, but Do you see any change with MCU expression or activity? No, no. Well, Juliana I think that Juliana Oropesa is hearing because she made a question. We asked her to prepare us a short herping MCU adenovirus to try to block it, but we don't check it now. Jessica Gambardella, did you evaluate the effects of CaMKII inhibitor or insulin resistance and blood pressure? Yes. We don't have changes in blood pressure with the model. In the model, I mean, the treated animals doesn't have hypertension. So we didn't check in the transgenic animals or under other treatment that was not fructose, but maybe we have to. Helen Collins, do you think there could be involvement of store-operated calcium channel mechanisms, STIM1 or I1, with the change in calcium you observe, or any potential post-translational modifications? Yes, could be. Yes, it's very possible, but we are not studying that. It's about Tanya Rainey. Do patients with diabetic mellitus have similar mitochondrial changes? If so, which type of diabetes mellitus, type 1 or 2 or both, is closer to what your observations? Okay, well, yes, there are similar changes in diabetes mellitus and type 2, because type 2 is 95 or more % of diabetes in the population. And we think that are more close to type 2 diabetes mellitus than type 1, because it's the model is with the diet, so we think that's that. So I don't know if I have to check the other chat, because
that was the last one. You went through 34 questions. This is fantastic. I can assure you that your mitochondria and sarcoplasmic reticulum are working quite properly. I mean, you are fantastic. You are terrific, my dear. I mean, such a high amount of energy. Amazing. Thank you very, very much. I mean, possibly the handling of questions was even more interesting than the presentation itself, because you gave us more data, more insights, more opinions, more future perspectives. Fantastic. Very, very well done. Congratulations.
Thank you, Fabio. Thank you very much. It's a hard work, and it's a work very fruitful, but collaboration. So I'm very happy to give my results here, because I think that all these questions trigger in me several future experiments. So I think to answer more questions next time.
Yeah, the more we work, the more we learn.
Yeah.
And I take the opportunity to thank Davor once again, and please give us your concluding remarks, Davor.
Well, I would like to thank both of you. I mean, for handling the questions exceptionally well, Julieta, for contributing fantastically, Fabio, to the discussions as well, and thank you for the audience for staying with us. I think, you know, an hour and a half is a long time to give up on a Thursday afternoon or morning. So thank you. I also apologize. I know there were some technical issues. The screens were jumping here and there. We will hopefully try and resolve that next week, but I'm pretty sure it hasn't been detrimental to the viewing pleasures. And again, thank you once again to both of you. And we will see everybody again tomorrow. And have a lovely day, evening, afternoon, morning, whatever time it is.
Thank you, Davor. Thank you, Fabio.
And thank you all the attendees. Thank you very, very
Yes.
much. It was a
Thank you very
terrific
much.
experience for me. Thank you.
Thank
Bye.
you. Bye.